Take a minute to appreciate the meme before we get started. It's a good way to deal with your test not passing. I'm a little tired this morning, I think. All right, so for the next 2 hours, we're going to talk about software testing. I'm going to give you a little bit of an intro on why you should write tests, different types of tests you can write for your code, and in which context you want to write them. You're going to get some practice writing tests for a piece of code that you've never seen before. And then we're going to go into some tools for testing, like stuff that you can use for your open source packages to run tests automatically. And then finish off with some best practices overall for testing. And then you'll get a chance to write tests for your actual repo. So just as a quick note, I'm going to use Piazza polling in this class. So just take a second to open up Piazza so you're ready to answer. All right. Okay, so the overall goals of this lesson is that by the end of the lesson, you'll be able to explain the difference between end-to-end and unit tests. You're going to understand why continuous integration systems add collaborative development, and you're going to be able to write tests based on anticipated use cases of your code. Okay, so starting off with why test. Testing is really crucial to a code's accuracy and flexibility. We all, as astronomers, test our code to some extent, meaning that anytime we write a script, we might run it and see that it's producing the correct output. But I think the step between writing tests and being a really excellent developer is spending most of your time writing tests. That's why we're spending 2 hours on testing today on the last day, second to last day of the workshop. Writing excellent tests is hard and requires creativity. You have to think about it a lot. Excellent developers try to anticipate and test as many use cases of their software as possible. Testing also ensures that your code maintains the same behavior over time. So if you have an extensive test suite and something changes in your code, your tests ideally should let you figure that out very quickly. So one of the goals for you today is to get in the habit of writing extensive and thorough tests. Okay, so now let's talk about different types of tests. In particular, we're going to talk about unit tests and end-to-end tests. Unit tests are tests that evaluate the correctness of individual elements of your code. So this is sort of like testing the smallest pieces of your code. Unit is the smallest testable part of any software. So you could think of this as like one function that might be part of a larger set of functions, or one method of a class, one error message, something like that. Unit tests generally have very few inputs and outputs. You're not going to run, several different functions in your code generally. You want to test very small parts of your code. So some examples of what to test. You can test the output of a function is correct for every type of input. You don't necessarily have to write one test per function. You can have several unit tests per function, depending on what the variety and the type of inputs you expect. It's also really important to include edge cases, and this is where a lot of the creativity and thinking about how could people possibly use this, and how could this function possibly break. So examples of edge cases are if your code operates on integers, make sure you're testing 0 or 1 or -1. If your code operates on strings containing star names, try non-standard strings like pi, mensae. A question we often get is, how do I test plotting code? A lot of our packages for astronomy end up having something that does plotting, and it's hard to test that your plotting code is running correctly without human intervention. So our suggestion is just to test that your plotting code doesn't fail. So apply these same thoughts about trying to test as many use cases as possible, but you're not going to be able to automatically check that you're getting the right code, the right plot. Just test that it works. It goes all the way through. Importantly, you don't need to test inputs that are not allowed by your documentation. So you don't need to test every possible way that somebody could, break your code if that's not something you're explicitly allowing. you want to think about, what am I allowing? How am I communicating that? And how could people break that? This is not to say that if you anticipate that like somebody might be confused by a common part of your code, that you could write an informative error message. So you could add something into your code that says, oh, hey, user, I know it says in the documentation that this input should be a string, but a lot of people often do integers instead. So you could raise an error message that says, hey, everyone, like, don't do that. Use a string instead. But in general, you don't need to test inputs that aren't allowed. Yeah, so here's an example. If your doc string says, one of the arguments is an integer, you don't need to test a float input. You can assume that your documentation is going to communicate to the user what they should do. So here's an example of a real unit test in the Orbitize test suite. I'm going to walk you through what this test is doing. So we're testing a function in Orbitize called RADEC to set PA. So this is RADEC is basically Cartesian coordinates, and set PA is what's it called? Polar coordinates, and we're converting between those. So that's all that function does in Orbitize. So you can see we've got a little doc string saying what this code does. It tests the basic functionality of this function for converting measurements in RADEC to set PA. So what we're doing here is we're initializing an array of RAs of right ascensions or X coordinates, an array of Y coordinates, and then I've got the expected position angles, the expected theta in the polar coordinate. I'm also testing this keyword of mod 180. So I want to check that, if I'm actually applying that keyword, that the expected PAs are also correct. And then also the separations that are expected, so the R in the polar coordinates. And then I'm actually calling the function. So I'm calling RADEC to set PA on this array of inputs. And then I'm calling it again using the mod 180 keyword. And then I'm using this series of assert statements in order to check that this is working correctly. So assert statements are your friends in writing unit tests. The behavior of a unit test is that the test should run all the way through if it passes, and it should raise an error. It should, the code should fail if the unit test doesn't work. Another little quirk of testing, especially when you're working with like numbers and conversions and stuff like that, so you can see I'm using this pytest.approx command here. Because of numerical precision, if we were to just say like assert that this is exactly equal to this, my computer might say, okay, there's a 10 to the minus 10 difference between these, so they're not exactly equal. So I'm going to say, okay, assert that they're approximately equal, and here's the absolute difference that I can allow between these. All right, so now your first Piazza question. What is an edge case that we should test for the RADEC to set PA function? So I'm gonna post this question on Piazza. Yeah, so you can see that the main way that I sort of handled this initially in this first version of this test was to put an RA and DEC in each of the 4 quadrants. So I had one in the quadrant 1, one in quadrant 2, quadrant 3, quadrant 4, and I wanted to check that that converted to the polar coordinates correctly in all cases. Awesome, thanks for your participation. Okay, so unit tests test the smallest little bits of a code. End-to-end tests are the opposite. These evaluate a code's ability to perform its intended functions. This is testing the code from start to finish. The things to think about for end-to-end tests are the overall performance and accuracy of a code's main functions. So if one of the main ways that your users will interact with your code is that they're going to get a posterior out, you want to test in your end-to-end tests that when you run the code following the instructions that you actually get the posterior you expect. You might want to test that the value of the posterior, maybe the median value of the posterior, is consistent with what you expect, either from an independent implementation or from one version of your code that you want to remain consistent over time. It's also important to test You don't necessarily, again, need to test like every possible way that someone could interact with your code. You want to test that the way that users will interact with your code, or the way it's intended for users to interact with your code, is actually going to work. So later in this lesson, we're going to talk about continuous integration, which is this practice of testing your code automatically every time a change is made. So these types of tests are not always amenable to continuous integration. So for Orbitize, for example, we maintain a set of end-to-end tests that are not run automatically. So they take a little bit longer. So we have them and we run them periodically, but we do it manually. We don't, and they tend to also require like human inspection of like making sure this plot actually looks like it's supposed to. All right, so here's one version of an end-to-end test in Orbitize that is fast and is amenable to continuous integration. So we have it in our test suite. So one of the main functions of Orbitize is to use a particular backend algorithm, it's called OFTI, to produce posteriors. And so we're going to, in this test, actually run OFTI, get a set of posteriors, and then compare it to what we expect from an independent implementation. So this is us setting up Orbitize for an actual run. This is us running the code and getting the set of posteriors. Then here I'm taking the median values of these posteriors, and then I'm using this assert statement to compare them to previously expected values. Yeah, so like running Orbitize the way that we expect users to interact with it and checking that the results are consistent. All right, so next Piazza poll, what's an example of an end-to-end test that's relevant for your research? All right, so the next step on our testing journey is I want to give you a quick tour of the tests in Orbitize, just to give you a sense of what different types of things we test, and how you can both to give you a sense of like what things we test, and then also to show you how we actually set this up in the repo. Okay, so if you go to the Orbitize landing page on GitHub, we go to our test directory here, which is in the same level as like the root directory. And it's the same level of the directory where all the code files, so the code files live one level above. So we go into tests. You can see we've got all of these individual files that start with test_.py. So these are all Python functions, Python files. These are vast majority unit tests. So if you go into a random one of test API, you can see we're testing the first one is testing the basic functionality of system compute model. So we're setting up everything, like setting up an initial version of an Orbitize run, creating an array of parameters, and then we're computing the model for those parameters. So if you think about it, imagine that we're fitting a line, we're giving it, M and B, and testing that it's computing the prediction of the line for those parameters. And then we're testing within this, we're asserting that the model shape is correct, that, and also for a different like type of parameter inputs, we're just testing that shape is now correct. So we're not doing anything fancy here. We're just saying like, okay, make sure that when you do this one function that the outputs look approximately right. We've got a bunch like this. I'll also show you where the end-to-end test that I just showed you lived. So that's in test OFTI. So we have got both end-to-end tests and unit tests in here. OFTI is an algorithm with several steps. So in here, we're testing the first step of that algorithm, which is one function within Orbitize. And we've got a bunch of assert statements in here, asserting that each step within that is also working correctly. And then we've also got a test of run sampler, which is actually doing that test that I showed you on the previous slide, of like running through an entire off-D iteration and checking that it agrees with these independently calculated values. But we've also got tests like this, which are very small unit tests. So I haven't gotten around to implementing something yet, and this is a common thing that users will like try to run, and so then they get so we added an error that says, hey, this isn't implemented yet. If you're interested, let me know if you want me to implement it. And so this entire test is just try to do that, and you know, try that, and then catch this not implemented error. And if we do that, then pass the test, basically. So this is how you would also like write a unit test to check that your error checking is working correctly within this try except statement. Yeah, I think that's all I wanted to show you. All right, so now I'm going to give you some practice actually writing tests, and hopefully this will help make the difference between unit tests and end-to-end tests a little bit more concrete too. So I'm going to give you 30 plus 15 minutes. The first 30 minutes, I want you to just work on this on your own. So give it with the actual instructions. I'll go to this link in a sec. Yeah, so 30 minutes to work on it on your own, and then 15 minutes to debrief with your group and go over your answers together. The purpose of this activity is to practice writing unit tests and end-to-end tests for an existing piece of code. Spend 30 minutes giving it an honest try on your own, but of course ask a TA if you feel stuck. Then the next 15 minutes discussing your solutions with your group mates. At the end, both you and your partner should have filled in the 2 unit tests and 1 end-to-end test. You might have different solutions, that's totally fine. And then at the end, I'm going to walk through my solution. So let's go to the link. I can show you what this looks like. So I've put together this little piece of code. Hopefully it's documented enough that you can understand what it's doing. So we are, the purpose of this is given some time series data, it's going to compute the sum of squared residuals for a linear fit and a quadratic fit, and then it selects the better fit and plots it. So we initialize this object, then we have one method of fitting a line, one method of fitting a quadratic, and then one method that plots the best fit. So what I want you to do is to first take a little bit of time to think about how this code is working and understand it. So answer this question of how a user might interact with this code, and then thinking about some edge cases. Then I've got some scaffolded unit tests and end-to-end tests for y'all to fill in. The first one, I've written out a couple of steps for you about how you would go about putting together this unit test for the fit line function specifically. Then next, I want you to come up with your own unit test and implement it. And then finally come up with an end-to-end test. And if you finish early, spoiler alert, this isn't the world's greatest code. It's sort of not great on purpose. So I want you to think about how you might improve the original code and make it better. And a hint of how to think about that and how to do it is how might you or a user break the code, and what can you do to decrease the probability of breakage. All right, hello everyone, welcome back. So I'm going to walk through some thoughts that I had about this activity. So first of all, the first question of how would a user interact with the code. So a couple ways I could think of is if they just want to fit a line, or if they just want to fit a quadratic function, they could just call those individual methods, and they could also do the full comparison and plot the best fit. Some edge cases that I came up with were if you have 0 data points, if you put an array of length 0, if you only have 1 data point, if you have all data points being 0, maybe that the data points define a vertical line with an undefined slope, how would the code handle that? There's tons more, but these are just some examples that I thought about that would be good to test. So here's what I filled in for the first unit test of test fit line. So it tests the least squares fit behavior of compare fitter.fit line, checks the fitted values and the residuals for a perfectly linear data set. So first, step one, I created this data set. I defined for some m and b and sometimes a set of data. And then I instantiated my class, and then I ran this fit line and checked that the fitted b was approximately equal to the input b that was used to generate the data set. Same thing with m, and also that the linear residuals were approximately 0, since this was a perfect line, it should have 0 residuals. Yep, question?
Yeah, so for a test like this, can you add arguments to test functions like this so like the user can change what the slope and intercept are?
Yeah, good question. So the question was, for a test like this, can you add arguments so that the user can change the like m and b that it could test? You can, but that would be harder to, you want to make sure that like your tests fully encapsulate everything. So like a computer can run through all of the tests and not necessarily need to like change things itself. So if I wanted to test like different values of m and b in this unit test framework, I would probably make different unit tests that would then be run. Yeah, good question. Yep, another question.
The PyTest method there, what's the sort of range on that? How does, that was one of the issues I run into when I did the test, is like, assert this equals to this, and it almost never was, because there's floating point errors. So what does the PyTest prox get us?
Yeah, so the question is, what's the like the limits of PyTest to prox? There's some absolute range that it has. I don't know what the default is, but if you don't specify it, I don't know. Do you know off the top of your head what the value is? Jason's Googling furiously.
I think it's just whatever your floating point limit is.
Makes sense.
Yeah.
Okay, sure. So that'll be OS specific, what your actual floating point limit is. I think it might, I don't know, but
1e minus 6.
There you go. Okay, 1e minus 6. So, and that's the absolute difference. So not like the fractional difference between the two values, but like, you know, if you have something to 6 decimal places and something else to 6 decimal places. But you can also change that keyword. I think it's abs, but we should check what that actually is.
There's abs and rel, depends on
okay.
relative or absolute.
Cool, thanks. So abs will be like if you want to check to 1e minus 8, if your computer, you know, can handle that. And then you can also do rel. So the rel, like if you divide them, what the relative difference between those two is. Does that answer your question?
Yeah, pretty much.
Okay, awesome, thanks. All right, so this was the first test. Notice also that I've got 3 different assert statements in this, so you don't necessarily have to have like one assert statement per test. So even though this is testing like one particular function, one unit of the code, we can check several things about that function. So I know that a lot of folks for this second one, it would sort of make the most logical sense to then test the fit quadratic, but I wanted to show you an example of how I would catch an error in a unit test, just to give you a little variety. So if I wanted to check if we have an array of empty times and empty data, if we're catching errors as expected. So I instantiated a new version of compare fitter with my empty times and empty data. I tried to fit the line, and then what's actually going to happen in this case is that the code is going to throw this type error. And so I'm trying and then accepting that type error. Notice that I'm only accepting type error. I'm not just doing this is correct syntax to just say try accept, but that will catch any type of error. So if your code breaks in any way, it'll catch that. So it's good to be specific about the type of error. So we're not just allowing anything to go through, we're allowing only this type error to be caught. And then for my end-to-end test, I'm testing the overall behavior of plot best for noisy quadratic data. So notice I'm making a couple of steps, a couple of like jumps in this end-to-end test. First of all, I'm testing like real data or closer to real data. So it's noisy. It doesn't necessarily have 0 residuals because I'm expecting that like my typical user will be using this to fit noisy data. So I'm generating noisy data here, and then I'm running the code as a user would. So I'm instantiating the compare fitter, I'm then fitting a line, then fitting the quadratic, and then plotting the best one. And so if I were to just run this through in a PyTest framework, it would just run, and I would just check that it's like actually like, you know, not failing, not producing any errors. But in an end-to-end test framework, where I would just like include this with the code and say, okay, every once in a while I'm going to run through this test and make sure that everything's running correctly, I would actually like manually inspect this and say, okay, that makes sense. The code is still functioning as expected. All right, and then some thoughts about the optional activity at the bottom of like how you would improve the code. So there are many potential things that you could do. I think a couple worth pointing out are that I think that it would be good to add a more descriptive error message for the empty array case, if that's something that we're deciding to handle. So right now you get, if you run if you run the code, NumPy polyfit won't be able to fit an empty array, and it'll say something like, what is it, an attribute error? No, type error. So it gives you a type error, like this type is not allowed by whatever, which isn't super informative to the user. It would be more helpful for me to throw an error that says something like, you know, compare fitter does not work on empty data sets or something like that. Another good improvement that would be good is that right now the code breaks if you don't run fit line and fit quadratic before plot best. So if we go look back at the code, you can see why that is. So if we were to just run plot best, you know, where is it? Yeah, so we're like assuming that these things, linear resids and quadratic resids, are defined, but those are only going to be defined if you run these first. And so the code would break if the user didn't run those in order. So I think it would be good to fix that or document it to improve the code. Another small improvement that we could think about is that right now the plot best is going to produce a plot every time, but we might not want a plot every time. Maybe we're running this in like script where we're going to do this for like 1,000 different data sets, and we want it to just, you know, print out what the best one is, or maybe write them all to a file or something like that. So it would be good to have a keyword that, you know, toggles on and off the plotting, so we can separate out the plotting, or better yet, to separate out the plotting and numerical comparison functionality, so that users can decide whether or not to do that. All right, cool. Well, thanks for participating. All right, so the next part of this lesson is taking you through some useful tools for doing your tests. So this part of the lesson is like, all right, you've written a really nice test suite, you've got all of these Python files. Now, how do you like incorporate it into your open source like workflow? So I've mentioned PyTest a couple of times. This is a really commonly used framework in Python library for doing tests. So it works, it's very simple. It basically just, the whole functionality of PyTest is to collect all functions beginning with test underscore in files called test_.py, and then just executes all of them, and then reports failures and warnings to the user. This might actually be familiar to all of you, because we had you run PyTest in order to check that your code Astro setup was working. So you ran the PyTest suite for Orbitize. So I'll show you what that looks like. All right, so here's Orbitize. We've got all our tests in this test suite here. You can see everything follows this, this naming convention that's required for PyTest. So all the files start with test underscore. And then inside of these files, we've got a bunch of functions that start with test underscore. So all we do to run the tests is, I'm right here, I'm in the root directory of Orbitize, and I'll just do py.test. The entire Orbitize test suite on my computer takes like 3 or 4 minutes to run. So I'm just going to test one test for now. So you can select one test, one file to run by just putting the name of the file after it. So you can see that it's collecting the test. So it's going through and looking for everything. And then it ran all of the functions in testapi.py. So you can see we've got 4 dots, and that's because we've got 4 functions that start with test underscore here. I guess I don't need to scroll through. You can trust me that there are 4. And then it'll give us any warnings that were output by these tests along the way. And then at the end, it'll say 4 pass, 3 warnings. We can also see what happens if one of our tests fails. So I'm just going to add in an assert false statement here. It's collecting the tests again. And so now it says, all right, well, 1 test failed. If we scroll up, it'll show you like which test failed and what line of the test failed and the error that it got. So this is really helpful for your users, and it's also helpful for services that you can like set up to run your tests automatically. The vast majority of like continuous integration, like automatic testing services, will work based on PyTest. Okay, let me go back to the slides. All right, so now let's talk a little bit about continuous integration. I've also mentioned this word a couple of times already. So continuous integration is a tool for maintaining your code's behavior over time. It's a development practice, and all that it means is just a suite of tests is run automatically every time a code is changed. So you can modify like exactly how often it's run based on your personal preference. It can be like, oh, I'm only going to run the tests every time a pull request to main is opened, or I'm going to do it every time a commit is made to any one of the branches on my code. Best practices for developing your continuous integration test suite is that your test should touch as much of your code as possible, meaning that like if you were to count up all of the lines that were run in the course of doing your continuous integration tests, it should be as much as possible. That said, there's definitely diminishing returns. There's sort of like, there are good and bad things. This is called coverage, like how much of your tests are covered by how much of your code is covered by your tests. The pursuit of 100% coverage is not necessarily the most rewarding exercise. It's more important to have tests that cover as much of the functionality of the code as possible, rather than like writing tons and tons of tests to make sure you get 100% coverage. It's important to keep in mind that you can have a suite of tests that has 100% coverage, but doesn't actually test the code in ways that are useful. So pursue useful tests that are creative and test the code and the functionality in ways that are helpful, and then secondarily pursue 100% coverage. All right, so I'm now going to take you on a tour of GitHub Actions, which is the continuous integration service that we use in Orbitize right now. We started using GitHub Actions about 2 years ago. So if you look at older versions of Code Astro, we take you on a tour of a service called Travis, which became not free, and so we didn't like it anymore. But now we use GitHub Actions, which is free. So let me show you what that looks like. So here's the Orbitize page again. If you go to this Actions tab on the top of the GitHub page, these are a series of automatic things that we've set up to do various tasks. We've got a couple. So we've got this page's build deployment is the thing that interfaces with read the docs and is going to automatically build our documentation using Sphinx, like you all set up yesterday. We've got a separate set of tests for just running through the Jupyter Notebook tutorials. And the reason that I separated those out from the continuous integration tests is that those take a little bit longer. And so I decided that we only want to run them every time someone's making a pull request to main, not on every commit. We've got a new one that compiles our JOS paper, and then also our suite of continuous integration tests. So it's relatively straightforward to set these up. There's a really nice like user interface that'll take you through it. If you just go to this Actions tab and you press New Workflow, it'll like direct you through how to set this all up. But I just want to show you what this actually looks like. So this is the latest version of our test that was run. We're running it. It's running 3 separate iterations of these tests on different versions of Python. So we're running it in Python 3.10, 3.11, and 3.12. And then in each one of these, it does a bunch of stuff to set up the environment that it's going to run in. And then it just runs PyTest. So this output within here looks exactly the same as what PyTest output would look like if you ran it in your terminal. And you can see at the bottom, we've got 97 tests passed. And then it also reports the coverage here. So we've got like for each individual function, we've got the percentage of the lines of code that were touched, and then the overall average percentage, the overall percentage of lines of code that were touched. So 86% coverage. 86% coverage is, we're very proud of that. It's pretty good. It's not, GitHub only gives you a green badge if you're over 90% coverage, which I have pursued relentlessly for years, but 86 seems to be about the best I can get.
Don't show them my 30% coverage then.
All right, and then there's a huge universe of tools out there that exist to control the environment of your tests. And I'm not gonna give you a super detailed intro, I just wanna point out some of them so that you're aware of them and you can learn more about them if you're interested. So Docker in particular is a tool for deploying applications inside these things called containers. They are more lightweight, meaning that they like take up less memory and space than virtual machines, which are these larger things that like fully emulate a like whole operating system. So if you want to like run your code inside of a Mac operating system, a Linux operating system, you can use virtual machines. But if you want to have this like lighter weight version of this that creates that you have some control over, but isn't like as large and expansive as a virtual machine, you can use Docker. If you do want to use virtual machines, Atveyor is another continuous integration service that will set up virtual machines and have your code run within them. I don't have a ton of experience with Atveyor, to be honest. I have more experience with Docker. The main advantage of using either of these services is that running inside one of these either containers or virtual machines means that no matter where you run the code, the environment is exactly the same. So setting up your like suite of tests to run within one of these environments can be good or bad, because maybe you know, if you're running, for example, a like data reduction pipeline, you know, you really want to control the environment. You want to make sure that everything is exactly the same every time you run it. On the other hand, if you're developing AstroPy and you want to make sure that your tools run on a variety of different OSs in a variety of different environments, you might want to like not set up your code to run inside of a Docker environment, for example. Or you might want to like set up many different Docker containers with different versions of the environments that you might encounter. All right, so at this point, I just want to open the floor up to all of you and ask you what you think the best practices for testing are. These can be, if you want to like repeat stuff that I've said already, feel free. And also, I know that you all have a lot of knowledge about this, so I want to encourage you to share your own thoughts that I haven't shared. And we're gonna make a list together, and then we'll have this forever. So if you're in person, you can raise your hand. If you're on Zoom, you can use Stack. So if you haven't used Stack before, the way it works is that if you have something to say, you say Stack, and then I'll call on you in the order that the stacks were stacked. And then if you don't want to wait for the conversation to get around back to you and you want to directly respond to something that was just said, you can type direct response, and that jumps you up the stack. All right, so floor is open. What are the best practices for testing? Yep.
Test as you go, not at the end.
Totally, yeah. So test as you go, not just at the end. Totally agree. Yep.
Build code that's modular and not something that's like elaborate.
Yeah, I really like that too, because you're talking about the way you build code being influenced by the expected testing behavior. So build modular code that is amenable to modular tests. Yeah, excellent. Other thoughts?
messages?
Totally, yeah, helpful error messages. So let's say build in and test helpful error messages. Let's build in. Yeah, thanks, awesome. Any thoughts from folks on Zoom? Or folks in person? Feel free to keep raising your hands.
Think of edge cases and or have someone else look at your code and think, like have fresh eyes.
Totally, yeah, I like both of those. So think of edge cases and then have other people run your code. Yeah, that's a really good point. And as I'm sure you'll all find out tomorrow, it's very different running your code on your computer than other people running your code, and you very quickly figure out all the different types of errors that are possible that you had no idea. Let's get like 2 more thoughts.
Keeping track of what you fixed with really descriptive commit messages, because
Totally, yeah. Keeping track of changes with descriptive commit messages. Our former TA, Simon, used to tell this story about how he was interviewing for a job one time, and his interviewer actually like had him go back to his past commit messages and was like, "What did you mean by blah, blah, blah?" And Simon was like, yeah, totally. We miss you, Simon. One more thought?
Also something you said, that every test cover as much of your code as possible.
Yep. So have your tests cover as much code as possible. I'll add without sacrificing making the test good. Without sacrificing. Is that it? Yeah. Writing good tests. Totally. Okay. Thanks, everyone. Thanks for your participation. I appreciate it. All right. So here's the list that I made, which I think is complementary to the list that already exists. So first, to test as many use cases of your code as possible, to write both unit tests and end-to-end tests. Something that was exactly said, write tests throughout the development process. Some developers even advocate for writing tests before you write code, and this is called test-driven development. I don't usually do that, but it's, yeah, so that's a thing that you can do. And then something that Jason taught me was turn debugging scripts into tests. So if somebody raises an issue on your code and they're like, oh, this isn't working, you usually end up writing something to debug it and fix it. And then once it's fixed, this debugging script should just work. So you can basically just take that and make it into an additional unit test. So practice that we follow a lot is to, like, if we fix a bug, just add a unit test to test for that specific bug. Again, like we were just talking about, coverage is important up to a point. It's more important to test your code in all the ways your users will apply it than to get 100% test coverage. And critically, 100% coverage does not mean no bugs. And then this is just sort of a piece of advice that I generally give to people that are interested in like working on a new piece of code for the first time, is to write tests for that code. And it's sort of like everybody wins. Like if you come up to a developer and you're like, hey, I wrote 5 new tests for your code, they'll be like, oh my God, my favorite person in the whole world, thank you so much. And it's also really good for you because you're going to be thinking about ways you can use the code. You're going to be digging into the guts of the code and really understanding how it works. Yeah, so that's my list. We can appreciate the meme. All right, so now we're going to take the next 20 minutes to start working on putting together the test suite for your package that you're working on. So I would encourage you to get together with your groups, write a couple unit tests and at least one end-to-end test for your package, and write your test following this PyTest framework. So make sure literally all you need to do is just make all your tests start with test underscore something .py, and then have all of your functions inside that be test underscore something. And then you should immediately be able to test it with PyTest and make sure that's working. And yeah, the output of this activity that you should start now and continue later is to push the code for your group's test to the group's GitHub repo. If you finish early, you can get GitHub Actions continuous integration set up so that you can actually run your test suite automatically. You could also explore services that control your environment like AppBear and Docker. And I've got a nice Docker tutorial here if you want to check it out.
All right, everyone. Let's get back and started again. So for our last topic, we're going to talk about anti-discriminatory practices, things that we can do to kind of to reduce the amount of discrimination in software development and software engineering in general. I'd like to preface this with some disclaimers. Is that we our instructors we're all based in the US, and we have a very international audience, and some of this stuff is pretty general. We try to make it as much general as possible. Some of it is US centric, and so just be wary of that. And the other caveat is I forgot to put in the slides is none of us we don't study like software ethics, AI ethics, or any of these things, right? Or just kind of just trying to distill information that we've learned and present that to you. So there might be things that we might not be exactly 100% accurate on, and that's because we're trying our best on this, but there might be we're much less experts. We're not experts on this. We're learning as I go, and also everything we present on this topic every year goes out of date next year. Because of how fast software development and software engineering has been moving technology-wise, especially with all this development in AI. So these slides have been constantly updated, and we've been trying to keep up, but sometimes we're a little bit behind just because of how fast technology moves. Okay, so let's just start off with just we should acknowledge that software engineering in general does contribute to discrimination in many different ways, and that we should always reflect on and assess how we're developing code and how we're doing it in a way that try to mitigate some of these effects. First, we're going to talk a bit about just like in general in the software engineering world, in the tech world, what's going on, and what ways can discrimination happen. First, let's talk about discrimination can happen in two different ways in terms of bias. And there could be both explicit bias and implicit bias. Explicit bias is conscious bias, where a discriminatory action is very intentional, clear, and overt. It's like that was the purpose. Whereas implicit bias or unconscious bias, when a discriminatory action is unintentional and the person doing it is generally unaware that it's happening. And both of these are happening right now, especially with all the new tools that are developed in the tech world. So if you just look at just who is doing software engineering, you can see that we have there's a clear evidence of discrimination in just like who are software developers, and you can see this in just like this is the Google releases an annual diversity report that shows demographics on their workforce, and you can see this is the diversity report back in 2020 on the left. And this is their workforce representation in 2024. So 4 years later, you can see that most things have not really changed. Software engineering is predominantly predominantly men, predominantly white or Asian, and you can see that the other demographics are in the U.S. Like I said, some of this is U.S. centric. In the U.S. is quite underrepresented, and you can see that even in the last 4 years, with like there's strong pushes for like social justice and improving some of these things, there've only been small gains in the in improving the representation at these big software industry, software tech giants. And some of the things are, the things that contribute to this sort of discriminatory behavior of who's actually working in software engineering. Those things are still happening, like sexism in hiring and promotion and pay is still happening. This idea of a culture fit, and who is like we want to hire people both for technical skill and they have the right culture of our tech startup or our tech company kind of thing. Those ideas are still prevalent and oftentimes discriminatory and exclusionary. And there's some links here if you want to read more about them. They're a little bit out of date, but I think are still relevant looking back at them in terms of what the general ideas they're covering are. But like there are reasons why we want to have, it's not just like we want to have diversity is not like, even like these companies know that they want to have that. Like Google is doing this not just from like, oh look, we're so good, we do no evil, which they no longer don't, and things like that. They just they said yes, have attack. Their mission goal used to be do no evil, and then they removed it in the last few years, which is why I made that joke. It's still the Wi-Fi password on the bus. Okay, good to know. But there's actually been studies, and many of these studies showing that diverse groups of individuals actually perform better. And there's been like even holistic studies at companies looking at companies that have more diverse representations, both in terms of race and gender, and finding that they actually are more profitable than companies that are less diverse. So they have financial incentive to promote these things, but they're still within the companies themselves, these inherent barriers that they're preventing diversity in these companies. Software in itself is also not unbiased. Sometimes people make the kind of the argument that software is just math, right? Math, how can math be biased? It's just doing like mathematical operations. But a lot of software is oftentimes is trained on data. So if you have biases in your input data set, those will be reflected in your output data set, because that's what your input data set is learning. These slides are we're adapting them because these things, like we first made these slides back in 2020, and this is what software bias was back in 2020. Is like we had back when Twitter pre-Elon Musk, and they had like Twitter pre-Elon Musk was cropping photos, and they will crop photos to like the most interesting section of the photo. So they did this test. Someone did this test where they had these two images of Lenny and Carl. So this is one image of Lenny and Carl where Carl's on top and Lenny's on the bottom. And the other image where Lenny's on top and Carl's at the bottom. And you can see this is Twitter's crop of both of those respective photos of what they think is most interesting, right? This is supposed to be an unbiased algorithm, right? It's just math, it's just training on what they think is interesting based on their input training set. But if their input training set is biased, then your output performance of your algorithm is also inherently biased. This is an example of implicit bias that's happening. Nowadays, there's ChatGPT is now the thing, and I think this is still very new research, and people are trying to understand what are the biases in these large language models. But this is one example where someone put in, or basically someone prompted it, please fill in the following analogy: X is to men as X is to women. X is to, please fill in the X. Man is to X as woman is to nurse. And then it like does this thing where man is to male nurse, whereas woman is to nurse, so you can see there's implicit biases and even in these large language models, even when they try to train them as, to be unbiased, they know there are still inherent biases in these models because of the training sets and what data is actually used, because we're using data from our society. So these machine learning algorithms are reflective of any biases that exist within our society, especially these things like ChatGPT are trained on the English language, on predominantly Western, culture, Western text. So you kind of get that reflected back models, in these large language models. And then these are some other links about, I think these are all getting old, but you can see there's a facial recognition systems, work best on white people and misidentify Black people. Uh, there's been lots of companies that predict crime based on previous police data. But if the previous police data is basically we sent officers to this neighborhood because we were discriminating against these people in the first place, then they just keep sending officers to those neighborhoods based on where they predict crime will be, and then they surely do. In fact, if you have officers there, they'll find more crime there. They're like, oh look, that neighborhood has more crime, so we keep sending more officers there, and then you get the systemic policing of various groups and unfairly, basically. So you kind of have this kind of positive or negative feedback loop in this instance. And then also inherently search algorithms themselves are biased. Yes. And then correcting biases is also not easy. So this is, it's not just like, here's like one thing we do and then we fix all the biases, right? Oh, like in the past, back in 2022, I showed this example of AI. So everything's out of date now. Back in 22, we're talking about DALL-E Mini. That was like all the hype back in 2022. I typed in, show me some pictures make me some pictures of astronomers at a conference. We can probably see some evidence for implicit bias in the pictures, or just how these photos, what kind of people are depicted in these photos, and we can see the racial and gender profiles are not very diverse, and this is a common issue back in 2022. So people were like, okay, let's just add an additional term in our training cost function, in our ability to basically force it to have a wider range of demographics in their training. So basically every set of images you output should have a diverse group of people of different genders and races. Like they just force that. And then you can, this is now what happened. This is what's happening this year. Like you basically, the new set of AI models now are forced to basically create people of different, when they ask to create images of photos, if photos of people, they'll create people of different diverse backgrounds. But maybe you don't want that all the time. So this is an example where people, this has been done to even more extreme cases where they ask to generate people from various members of various hate groups and things like that. But like here's a more tame one where they're asking to generate pictures of US senators from the 1800s, and we probably know what the demographics of US senators from the 1800s are. And this is like just forcing that every set of things needs to have a wide range of possible diverse options may not always be what you want either. So it's correcting the biases in the machine learning models also requires subtlety, and right now all of it's done kind of with the entire public as kind of the guinea pigs. So that's kind of what's going on right now. We have to be aware of these things and recognize kind of what's the state of these very powerful but potentially very dangerous tools. And they are being used in very nefarious ways. So just because we've written these amazing tools that can do these amazing things, some of which are very good, like they can help us code, help us write things, write things or parse things that we don't really want to read, summarize things. They can also be used in very nefarious ways. So these are evident ways for explicit bias. And I've literally every year had to append more things to this description. So like fake news is now happening as being spread using very efficient advertising platforms that have all of everyone's data, knows everyone's demographics and targets people, and able to infer who's more susceptible to what kind of advertising. But now also that fake news is now being written by generative AI models like ChatGPT, so producing more and more content, like fake news content, at a faster rate than ever before. And so these are ways that these tools that were originally built, like Facebook for social networks, ChatGPT for whatever ChatGPT was built for, to basically use in, but there are these very powerful tools that can now be used in very nefarious ways to kind of subvert various existing structures. Another one is, especially with these generative AI models, is deep fake videos of prominent individuals. Like there's a lot of people out there with a lot of data on themselves. You know, they have a lot of recordings. Like basically, if you've heard them utter like every single syllable they could have possibly uttered, you've seen like every facial feature they could have probably made, and that's all gone into training and basically produce fake content that of people that never existed. This happens in popular culture. You know, maybe some people enjoy that, but it's also happening to very prominent political figures saying things that they've never said, basically. And people are now doing studies trying to keep up with this, like how much, like you can see most of these deep fake videos are done for impersonation, but you can see there's a variety of different ways people are using these deep fake videos, this new technology, in ways that are explicitly, you know, causing harm, basically, or causing trying to consciously doing discriminatory actions. And then kind of closer to kind of programming, there are also issues with, you know, there are things like GitHub Copilot. We've also maybe encountered like Google Gemini is able to program for you. Like if you give it, say if you give it a doc string, like please parse a list of expenses and return the list of tuple, date, value, and currency. Ignore lines starting with this pound sign, and parse using the example data below. Google, like GitHub Copilot will just create all that code for you. So this is like if you're encountering procedural code that, you know, it'll take you some time to write and physically type it, you know, Google Copilot can like in like a few seconds spit out all that code for you in a correct way and something that works. So this is very powerful, and you know, it's not saying you shouldn't use this, because it's going to help a lot of people in their daily lives doing very routine things, especially, you know, very mundane like list parsing things that you're like, oh, I have to write all this code, it's going to take me like 20 lines, but like it can just do it for you automatically once you explain to it what you need to do. But there are still issues with these things. GitHub Copilot works by training itself against all the public GitHub repositories that exist out there. So it looks at all the code, looks at what it does, and basically learns from all that how to code itself. But like, you know, it doesn't really think about what are the licensing requirements for the code that it learns. It's just saying that its justifications that we don't care about licensing because it's not actually going to return the exact same code as any of those packages is learning. It's just reading those code packages which are publicly available for everyone and learning itself how to code. But that's not actually true. Researchers have found that 1% of Copilot snippets have basically code snippets with more than 150 characters straight that match exactly its input training data. So it's basically outputting exactly what it's learning. And you know, at what point does that become a copyright infringement? At what point should developers be getting credit? Like if a for-profit company like Microsoft is using it to produce code and earning billions of dollars, should these developers who release their code open source online that help make these tools possible be earning some of that money? So this is stuff that's happening in court, and people are trying to figure out, you know, is this a thing? And you could think about also, you know, who's this benefiting? If these big corporations are making money, who's actually financially benefiting from these big corporations making money, such as the stockholders, and how does that and then whose efforts being used, like who's actually who are all these open source developers, and maybe, you know, those two groups have, you know, different demographics, and one is benefiting directly from the free labor of the other. Okay, so these are, you know, big picture societal issues. You know, it's not something we can address in Code Astro ourselves, but you know, there are things, you know, we can do. You know, these tools do provide clear, tangible benefits. It's not like we should outlaw these tools 100%. I think clearly there's evidence that regulation of some sort is needed. Government legislation in general is slow compared to the speed of development. That's something that we have to face. I mean, things that I kind of came up with for, you know, what we can do ourselves, you know, we can be judicious for how we use these tools and what they produce, being critically understanding, what is like I understanding like this tool is helping me, but in what way should I trust its output? In what way should I, edit what it's actually producing, and understanding the biases that are intrinsic to these tools. We can always advocate to advocate for more oversight. Make that something that you're aware of. Make something that if you have, if you live somewhere with you can influence your legislators. That's make something that they're also aware of. And we can also teach others about these issues, bring them to awareness, and make other people kind of understand what are the possible biases people just may not have thought about them, right? They just have this cool tool, it works, they want to learn about how it works, but maybe they should also learn a bit about, what are the possible issues with these tools. Okay, so that's kind of big picture. Let's come back down to like what we can do. So let's talk about coding, like coding in astronomy now. So like software development in astronomy. Like if we're developing an open source package, what can we do? How can we avoid contributing to an exclusionary culture in our own field? Let's go from very big to our very small field of software engineering and astronomy. Something that we think we have influence over. So some ideas I came up with, don't no language hate, don't tell people like, oh, I can't believe you're using IDL for that. Python is, or Julia is so much better than IDL for this task. Don't micromanage other people's code. I think this is similar to like the backseat driving thing we were talking about earlier. Oh, you should be using iterators to do that instead of a for loop or something like that. Don't minimize what other people are trying to do. People all come in from all different kinds of career stages. Like it's trivial to do X and Y. Maybe I think we have a little bit of time, so let's take a few minutes to try to brainstorm other ideas for how to not avoid contributing to an exclusionary culture. So for folks on Zoom, feel free to post things in the chat, and folks in person, I guess feel free to raise hands, and let's try to maybe add a few more bullet points here. Maybe think about like your own experiences, what are things are there cases in where you felt excluded? Are there cases you saw other people participate in exclusionary behaviors, and like how could we avoid doing that in the future? Take a few moments, think. Yes. Mm-hmm. Recruiting, contributing to code. I cannot spell, so it's gonna be like that. That's a great one. Yeah, I think one of the great thing is actually having in your repository how to contribute to this repository. Like especially like if you want to contribute message blah, or like make a pull request, like make a new branch and do a pull request on X. Things like that to show like exactly for people how can they contribute. Yeah, it's a great one. Back there. Coding. That's right. Coding environments are just a tool. So whatever gets the job done, gets the job done. Great one. Others? Yeah. Everyone knows everything, but they can learn it. Good.
Not everyone needs to know how to do everything.
Mhm.
The diversity of skill set.
Exactly. That's one of the benefits of open source development is, various people with various skills all come together and put their various expertise together to make something greater than the sum of its parts. Okay. Any last one? Anyone on Zoom? Yeah. Yes, grid one, give credit where credit is due. Yeah, recognizing the contributions of everyone involved. That's a big one, especially in a field like academia where credit and reputation is so powerful in our field. Being crediting people is very important for what we do. All right, this is great. So we'll keep this list here for everyone to reference. And here's a few things I thought of. So we'll go through a few kind of small things that we can be doing. One is replacing discriminatory language in our code. So you'll see some various terms in programming we try to avoid using. So here's some of them are this. They don't really generally these terms are not very precise. They come from, generally discriminatory backgrounds, and they're not particularly useful. So we've replaced them. So like this idea of when you have like a primary and a backup kind of service, like one being the lead and one being the follower, they used to be called master and slave. Also, for like if you want to block or allow various like say like IP addresses or users, they used to be called blacklist, whitelist. These are all especially in astronomy, there's a real software package called Source Extractor that is abbreviated in that way for very explicit like discriminatory purposes. Like the creator of the package refuses to rename the package because they're like, I like it this way. So people nowadays use a different abbreviation for it because it was just like there's no reason for it to be that way. And so as a community, even if the lead developer says I refuse to, we can still adopt other naming conventions for things, and as a community, that can become the norm. And in general, like I said, these discriminatory language they're not very precise. And oftentimes make the code more difficult to understand because they're not actually saying what the main purpose of this is. Whereas you can use much more descriptive language. Yeah. So do use descriptive and professional variable names, and also don't use swear words. It's one of my personal pet peeves. So code is kind of the face of your software, right? So like it's like if someone were reading your paper, would you be putting swear words in your paper, basically? Like the same thing, or other kind of various offhand comments in your paper. Code, like when people are reading your code, that's that when you're publishing your code, that's what people see. Bad variable names can make other people feel uncomfortable, and in general, just clear variable names make your code easier to understand. So like sometimes it's just easy to write something that's like maybe not so great of a variable name just because it's vague and you don't have to think about it. But take a little bit of time. Like sometimes you're like, this thing just does a bunch of stuff. Like I've made some, these are pretty tame. I don't want to go very extreme. I just call it stuff, right? You can imagine this could be worse. I'm gonna call this a stuff because I don't really want to spend effort. But like if you take the time and just be like, this is the helper function for this other function, transform coordinate helper, and like that's way more informative and useful than just like stuff or something worse than stuff. Same thing with trash. Something you're like this variable name does nothing. I just have to name it something because I need to define this variable name. If you have an unused variable name that just like is being outputted by a function, no matter that you can't control, the Python style guide says a single underscore is what you should be using. So if you have something, so you have a function that outputs 4 things, you only want one of them, you can literally have your variable name for the one thing and then do like underscore 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 for the other things, right? That's way better than just like calling it random words. Same thing for like temporary variables. It's like give it a little bit, spend a little bit of time, give it a little bit of definition, and they'll be better than just like having people to read whatever random words you come up with. Just like why would people read this in a paper? In the same thing. Be inclusive in your software collaborations. And this really goes back to the idea of credit as well. If you're using code from someone else, you should cite them, or if you can't cite them because their code hasn't been published, maybe you should offer authorship to them. If they developed or fixed something just for you, maybe you should, like, even if it's an open source package that you could just download for free, maybe you should still offer them authorship for having helped you specifically. pay attention to whose ideas get noticed and credited. This is oftentimes where in the past, in the history, you can see instances of discriminatory behavior happening. There's a very good example of that from physics. You can read this article is about the women who did the computation behind the discovery of chaos theory, and basically until recently their contributions weren't known or recognized at all, basically because they even though they did a lot of the work, they weren't credited with that discovery. Maintain open and respectful communication with your team members. I think that's and one of the examples of that is to value collaboration over being like absolutely right. If someone provides a solution, it's a pretty good solution, but you think, I can adjust it. Like you don't want to micromanage everything someone is doing, right? You have trust in them to do something, and then there are ways like a formal code review for someone. You can offer some of these things. Don't like micromanage them in every step. If they're like, oh, I think this is roughly the right thing to do, like, great, that's roughly keep doing that. And then, maybe I can try to adjust you afterwards, but like, let them cook basically. Learning the new lingo. Iteration is important. It's always, not everything we do is perfect. Even here in Code Astro, we're always seeking for improvements. So, seek feedback on your processes, your norms, and your code, and look for ways to improve. And then there's also, how do we address when there is discriminatory behavior happening in software development? You can redirect it to a more constructive action and change the attitude. So if someone is, using variable names that are making you uncomfortable, you can ask them, could you make your variable names more descriptive? I have a hard time understanding what your code is saying. If someone's like, oh, this is trivial to do, blah, you should just do this. It's super trivial. And you're like, okay, if you're familiar with how to do this, could you provide me as an example or a code snippet to get started? Redirect something, a comment to a more constructive action. If you feel like you're comfortable doing so, call out discriminatory actions. Oftentimes they're implicit and unaware. So it just might be something that they didn't realize that they were doing. Writing a code of conduct for your software package, especially once it grows beyond maybe this one or two developers, is a very useful thing. It explicitly states what is allowed and not allowed. It states the consequences for violating the code of conduct. You can check out our Orbitize community agreement for an example of a software package with a code of conduct and how it's written. And in general, discriminatory behavior in software should be treated like any other professional discriminatory behavior happening in the field, and your institutions hopefully should have resources and guidelines for handling these incidents. All right, so that's just a summary of the things I talked about. Use professional and descriptive variable names, write clear contribution guidelines. Actually, these are not a summary. These are just things. Write clear contribution guidelines. I think that was suggested as one of the ideas here. Keep track and recognize your contributors. Like, for example, in Orbitize, we have a change log. So every time new changes happen, we write out all the changes, and we also say who made those changes. So it's very clear who has made contributions to the code. For larger packages, draft rules for the entire developer community, and then credit the authors of the packages you use in your code and in your papers. Lastly, I just wanted to say one thing about environmental considerations. Some of us, we run very computationally intensive pieces of code, and we should think about our energy footprint. Oftentimes, the folks that are doing the large computations, we live in a very privileged society, and that we may not, but we're producing emissions that will impact the whole world, in which less privileged societies may feel more of an impact of. And it really depends on supercomputing could be either a very large or a somewhat less significant part of your astronomer footprint. It really depends on the country you live in. For example, in Australia, where there's a lot of coal burning fossil fuel plants, supercomputing is a large amount of the average emissions for an astronomer per year. So you can see a typical US household emits about 7 tons of carbon dioxide per year. a typical astronomer average over all this, the mean CO2 emission per astronomer is about 15 kilotons of CO2 per year just from supercomputing alone. Whereas if you look at somewhere like the Netherlands, that number is much smaller because a lot of the energy generation is being done through renewable resources. So thinking about where our energy comes from, how much time we're actually using on supercomputers, how much resources we're actually using, and who's benefiting from the computing time, and who's being impacted from the emissions that we're creating, something we should also be aware of. Okay, that's everything for this section. That's the end of the lessons for Code Astro. So hope everything has been informative. Just to remind folks, please sign up for project presentations. Please please fill out that form to add your Code Astro project to that project database. And then you have all today, the rest of the day until tomorrow morning to work on your projects, and then we'll do our industry panel, and then I'm excited to see what y'all created, because I see some really promising stuff. So I'm really excited to really looking forward to it. Okay, so let's break here. Thanks for everyone for joining the synchronous session.